Let's talk about half-life. Half-life is the time required for half of a sample, a radioactive sample, to decay. It's a way to measure how fast it is emitting particles or how slow in comparison. And each atom has a particular or unique half-life. Here's a half-life graph, and this is a very typical question, and the question would be, what is the half-life of this substance? So this is cesium-137. How you read the chart is you, first of all, notice how much of the material that there is. And it says 100. It doesn't say if it's 100 grams or 100%. It doesn't really matter. What's important is that you take the maximum amount that's on the chart and then you go to the halfway point. So if we're at 100, we would go to 50. Then you read across, and right at where it intersects the line, you're going to read down and look at the time. So on this chart, I would say that the half-life is 30 years. All right, now what is happening here? So after 30 years, half of that radioactive material has become something else. It hasn't disappeared, it's just become something else. What will happen in another 30 years or at 60 years? Well, you would see that it would drop to a quarter of the original sample. Here are two examples of two radioactive samples. We have one that has a half-life of 1.2 minutes. So that means after about a minute, half of that material has become something else. And here we have uranium-238. Its half-life is in the billions of years. So you can see there's a wide variety of radioactive particles, and it's just through experimentation to figure out what their half-life is. Obviously, somebody's not going to wait around for a billion years, but doing the math, this is what the half-life ends up being. So you should know that the decay is constant, but it is random. So it's not like it is shooting out a particle every second or so. It's very, very random. But when you look at the average amount of particles that are flinging out of the nucleus, and so your nucleus is becoming a different element, you will see that it is consistent, but it is random. And it also doesn't happen all at once. It's not like in that last example, we got to 30 years and boom, half of it decayed. No, it's consistent and constant. And again, it does not disappear, it just becomes something else. Let's look at how we do half-life problems. So I'm going to do these half-life problems two ways, and you can pick whichever way you feel comfortable doing. The chart method is what I'm going to do first. Sometimes it takes a little bit longer to do the chart method, and there are more opportunities to make mistakes, but you can still get the correct answer with the chart method. There's a couple of things that you need to keep in mind. First of all, you're going to make yourself a little chart. Time is going to go in one of the columns, and it really doesn't matter which one. And then you're going to compare it to the amount. The secret of the chart method is always start with a time of 0. That is very, very important. And then for the amount, whatever the problem says, you're going to put the starting amount there. So our starting amount in this case is 100 grams. All right. Next, we're going to look and see what the half-life is. So if they tell us the half-life, we can put down for our time, after one half-life, which in this case is 10 years, we're going to see that the amount of material cuts in half. So this, all we're doing here is we're dividing our amount by 2, and on the left-hand side, we are counting by half-lives. So a half-life goes by, that means 10 years. Let's have another half-life go by. So our half-life again is 10 years, so that means we're at 20. So here's our another half-life. And you don't have to draw those arrows, I'm just showing that's what we're doing. We're counting by tens there. And then on this other column, we're dividing through by 2, so we end up with 25 grams now. Let's go ahead and do another half-life because it's asking about 30 years and we haven't quite got to that yet. So let's do another half-life. So now we're at 30 years. And what is the amount? Again, we divide through by 2 and we're going to get 12.5. So this is our answer, 12.5 grams. All right, so this is using the chart method again. Have two columns, the time and the amount. The time, make sure you always start at 0. And then you just line it up. On the time side, you count by half-lives. On the amount side, you divide by 2 until you get the answer that they want. All right, let's look at the same problem, but using the little simple formula. So our formula is right here. You take the original sample, so however many atoms you have or how many grams you have, and then you're going to multiply it by 1/2 times, 1/2 raised to the number of half-lives that have gone by. So let's look at the same problem that we just solved with the chart, but now let's do it with this little simple math problem. So our first thing that we need to do is we need to find the number of half-lives. So to find the number of half-lives, we see that we want 30 years to go by. So in that 30 years, how many half-lives went by? Well, my half-life is 10 years. So 10 years is equal to 1 half-life. So years will cancel and I can multiply through. 30 times 1 divided by 10, and I get 3 half-lives. And you should always get a whole number. If it's something that's really close, like 3.99, obviously that would be 4. So it should be a whole number. So then we have the original sample, and the original sample is 100 grams. And then I'm going to multiply it by 1/2 raised to the third. Again, the 3 is the number of half-lives go by. Well, if we recall in math, 1/2 times 1/2 times 1/2, that would be 1/8. So that's our fraction of how much of the sample will be left. So we should have 1/8 of the sample left. So 1/8 times 100 grams, and we get 12.5 grams. So this is how you solve half-life using this little simple math formula.